Alright guys, let's start vodcast 6.1. We're going to start our new unit, which is on bonding. And so, of course, as usual, the first section here will be a little bit on how we get to the idea of bonding. We're going to start out with a familiar concept. We're going to start with the idea of valence electrons. And if you recall, we talked about valence electrons at the end of the last unit. And remember that valence electrons are just those electrons that are in the outermost energy level. Okay, and it has to be the outermost occupied energy level. It has to have some electrons in it. But those are the electrons in that outermost level. So that electron and that one, in this particular case, I would have two valence electrons. Okay, so remember, hopefully you'll remember that idea pretty quickly. If we look at the periodic table, we can sort of remember how we found the valence electrons. Remember that we sort of numbered the S and the P block from 1 to 8. Remember, we skip the D block. Don't worry about the F block. And then we count across on the periodic table to find whatever element we're looking for, and that's how many valence electrons it has. So, for instance, if we're looking for phosphorus, we start over here and we say, okay, 1, 2, 3, 4, 5, and so I've got 5 valence electrons. If I was doing, say, germanium here, 1, 2, skip the D block, okay, and then start again on 3, 3, 4 electrons. Or we could count backwards from 8, 8, 5, or 8, 5, 8, 7, 6, 5, 4, and we'd still have 4 valence electrons for germanium. Okay, so we did that in the last lesson, and we did a worksheet on that. Hopefully you should find that pretty easy. Now remember that what we're trying to get to, that all of the atoms want to get to, and this is really important for us in bonding, is that all the atoms want to get to a noble gas electron configuration. Okay, and we're going to talk about how we get to that a little bit more here in a second. But remember, if we look at our normal electron configurations, that we can tell the valence electrons here also by looking at the coefficients. Okay, remember coefficients are the beginning numbers. Okay, so the 2s, 3s, 1s, 4s, and the highest one of those, okay, which in this case would be 4, that's the highest energy level, and so however many electrons are in that, that's how many electrons we have. So we have 2 valence electrons in this case. Okay, now to get to noble gas electron configuration, remember, and this is the idea that we talked about in the last section, that we want to get to have 8, which is the octet rule. To do that, all we would have to do in this case is we would lose these 2 electrons. Okay? Now, why would I want to lose those 2? Remember, this goes back to ionization energy. If we can get rid of those 2 electrons, then here's what that's going to do. If I drop those 2 electrons, my new electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. 3p, oh, let's erase that. Okay, 3p6. And so if we look at what is our highest energy levels now, it's the 3s. Okay, and remember we got 2 of them. It's always the S and the P if you have both of them. And so we're going to add up 2 and 6, and that's going to give us 8 valence electrons. Okay, now why is that important? Because 8 valence electrons gives us a noble gas electron configuration. Remember, all of the noble gases, okay, if we go back and look at the periodic table, all of the noble gases, remember the noble gases are right here, okay, they're group 18, they all have 8 valence electrons, except for helium. Remember, helium's a little bit of an exception, it only has 2, but that's because it's only in the s orbital area. But for most of them, they've got 8, and so that's what we're trying to get to, are those 8 valence electrons. Okay? Now, a good way to keep track of this is something that we call Lewis dot structures. And you may have done these in biology or maybe even in physical science. They're pretty easy to get to, and here's the way that we do it. The first thing you do is you write down the symbol of the element, so we're going to do chlorine. Okay? You find out how many valence electrons it has. Chlorine has 7 valence electrons. If you're not real sure where that came from, pop back at the table. Okay? Chlorine's right here. So 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay? So chlorine's got 7 valence electrons. And then what you do is you're going to draw dots around the symbol to represent the electrons. And the way it works is that you always start at the top and you put one around each side, okay, going clockwise, which means around this way. And then when I get back to the top, I put the second one in, okay? So that's 6 and 7. And so total, I have 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay, this is going to be real useful to us when we actually start to draw bonds here in a minute. So real quick, let's run through a few of these just to make sure that we can draw Lewis dot structures. So get out your periodic tables if you don't already have them, and we're just going to run through real quick and draw draw Lewis dot structures for each of these. Okay, so sodium has 1 valence electron. Okay, and you might want to hit pause between each of these and try to do it yourself just to make sure that you fully understand what's going on here. So aluminum has 3 valence electrons, so we put 3 dots there for aluminum. Nitrogen has 5. Okay, remember we put 1 around each side. Then we come back to the top, so that's 5 valence electrons for nitrogen. Calcium has 2. Okay, sulfur has 6. So 1, 2, 3, whoops, sorry, I didn't follow my own rules. It's because I knew how it was going to turn out. It should look like that. It's got 6 valence electrons. Okay, fluorine, 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay, oxygen has 1, 2, 3, 4, sorry guys, I counted wrong again. Something about oxygen and sulfur, since I know they're going to end up with 6, but they've got 6 each. Okay. Neon, now neon is a noble gas, so unless it's helium, you like that voice crack in there? Unless it's helium, you know how many it's going to have, which is 8. I mean, noble gases have 8. That's why they're noble, okay, because they're satisfying the octet rule right then. And carbon has, of course, 4, which means it has 1 in each area, which has a lot to do with all of the bonding and stuff that goes on. There's a whole class of chemical compounds called organic compounds, not to do with the type of food without pesticides, doesn't have anything to do with that, but organic compounds all start with carbon, and that's because carbon has this peculiar structure where it's got 4 single electrons. We'll get to that a little bit later. Okay, so check those, make sure you got all those. We'll do a worksheet on that to make sure you got it, but drawing Lewis dot structure is pretty simple. So that all leads us to then what is a chemical bond. And so here's the definition. Again, as with a lot of times, this is sort of a technical scientific definition, but basically a chemical bond is just a force that holds a bunch of atoms together and makes them one thing together. So instead of it being a sodium and a chlorine and they act differently, so like sodium is a sort of really reactive metal. You saw the videos we saw before where it flares up and flames up, and then chlorine by itself is a poisonous gas. But you put those two things together, okay, so sodium and chlorine, but you put those things together in a chemical compound to form NaCl, and NaCl is table salt. Okay, so you got really explosive metal, poisonous gas, put them together, and you get table salt. And so the reason that they act differently then is because they are chemically bonded together. And so the chemical bond makes them act as one thing together, okay? It makes them function as a unit together. Now, there are different kinds of bonds, and here's what's important, and we talked about this term before. Electronegativity, this was in the end of the last section. Remember, electronegativity is how bad it wants electrons. The electronegativity determines what kind of bond it is. So these are the sort of types of bonds. In general, there's two big categories. There are ionic, okay, ionic bonds that have a really big electronegativity difference, and then over here on the other side we have covalent bonds, okay, where there's not much of a difference in electronegativity. Now, if there is some difference, then they're what we call polar covalent bonds, okay, and if there is no difference, then we call them nonpolar. We'll get a little bit more into that in another video. But what's important for us now is to recognize that there are two overall types of bonds, okay, ionic, well, that didn't work at all, ionic and covalent. So how do we tell the difference between those two things? Well, here's the way it works. An ionic compound or ionic bonds exist in compounds where you have a metal and a nonmetal, or a polyatomic ion. And we'll talk here in a little bit about what polyatomic ions are. But here's the big kicker. If it has a metal, it's always ionic. Okay? Now, the question then becomes, how do you know if it has a metal or not? Okay, so to do that, we're going to go back to our periodic table. And if you recall, we've done this tons of times now, there is a staircase here on your periodic table. Okay? Right here, right underneath boron. And if you remember, everything to the right, everything here to the right of this line is a non-metal. Okay? Everything to the left of the line is a metal. Okay? So that means that this whole side of the table, everything here, this includes the F block, by the way, because remember the F block slides up right in here. Everything on this side of the table is a metal. Everything on this side of the table is a non-metal. And you're thinking, well, almost everything's going to have metals in it, right? That's most of the table. Actually, no. In any compound, you're only going to have one metal in it, and the other thing is pretty much going to have to be a non-metal. So let's real quick look back at what we just looked, the compounds that we just had. We had lithium and fluorine, okay? Or lithium fluoride, it would really be. Lithium over here on the left side, so that makes it a metal. Fluorine's over here on the right side, so that makes it a non-metal. And so we go back to types of compounds. Lithium fluoride is going to be an ionic compound because it has a metal and a non-metal. Okay. We look at calcium chloride. Jump over to our periodic table. Calcium. Okay. Chlorine. Calcium is a metal. Okay. And chlorine is a non-metal. And really, you don't even have to worry too much about saying metal, non-metal. As soon as you see a metal, it's ionic. Okay. A single metal makes the whole thing ionic. You don't have to sit there and stress and go, okay, what's the other thing? If the first thing is a metal, then it's going to be ionic. Okay? Conversely, if you've got non-metals, if everything in it is a non-metal, then it's what we call a molecular compound, and the bonds are what we call covalent. So carbon and chlorine, both non-metals, both to the right of the staircase, so that's a molecular compound. Nitrogen and oxygen, look on your periodic tables again, nitrogen, oxygen, both non-metals, and therefore those are both covalent compounds. Okay, so let's just run through a couple others real quick. If you want to hit pause and just try these out yourself, you can. These are pretty simple, but here's the way it works. Whoops. So if you look at these, sodium is a metal. Okay, so as soon as I see metal, I say, great, that's ionic. Okay. The next compound, phosphorus and chlorine, those are both non-metals. And so that means this is covalent, or we could say that it is a molecular compound. Either way would be fine. The bonds are covalent, the compound is molecular. Carbon, hydrogen, and oxygen, all non-metals. So that makes it covalent. Now you're thinking to yourself, well, I'm looking at my periodic table, Arnold, and actually hydrogen's way over there on the left side. Doesn't that make this a ionic compound? Isn't hydrogen a metal? Hydrogen is an exception. Okay, hydrogen is a non-metal. Okay, so whenever you use it in a compound, it does not classify as a metal. Now, in some ways, it does act like a metal, but we're just in general going to treat it as a non-metal. So that makes that compound still covalent. In our last compound here, potassium permanganate, potassium is a metal. Okay, and as soon as I see metal, I immediately sort of scream out to myself, hey, that's ionic. Okay, so hopefully you guys got that. We'll run through some practice today in class, and I'm pretty sure that everyone will get a pretty quick handle on that, guys. Thanks a lot.